observe, we learn this, we observe 1 minute silence. Which means be absolutely still and quiet. Close your eyes if you wish. Every class we relax and then we start. Okay? Keep quiet. Okay. I want to start with the question which you asked in the last class. What's the difference between strong and stiff? Very good question. I've drawn here two curves, typical curves, and I've just written P and delta. Now, you should ask, what P, what delta, what's the structure? Well, this is a generic graph which holds good for beam, frame. So you have a load P and you have a deflection delta in the direction of P. Not necessarily at the same location as P. For example, in a building, it could be, delta could be at the top. So typically you could get a load deflection behavior like this. I've drawn two lines, one is yellow, the other is orange. The question is very simple. Which one is stronger, which one is stiffer? Which one is stronger?
It is clear that
No, it's
yellow.
I want it to be very clear. Yellow is stronger because its strength refers to the ultimate load resisting capacity. It could be flexural strength, it could be shear strength, it could be any strength.
Okay.
So this is certainly stronger in the sense it can resist a higher load before collapse. Whereas stiffness relates to
load per unit.
Now, can you talk about stiffness for either of these two lines? You have to be careful. The word stiffness.
That is only initial portion, then later on it collapses.
So we have typically, service. We have ultimate. If I take the yellow line, this is ultimate. Service is much lower because this is an extreme load. Right? It's an extreme load and the element or structure is going to collapse at that load. Whereas service loads are usually somewhere here. You should call it W. So service or sometimes we say work. You get it? Now usually you do your structural analysis using, nowadays everybody uses software, finite element analysis. That analysis assumes linear elastic behavior, which is more or less justified up to service. Maybe a little beyond service. In concrete, you will get non-linearity even before that. We'll discuss that later. So, if this is your service load, your stiffness is usually a reference made. You can talk of stiffness at any load level. But once you have a non-linear behavior, then you really can't talk of stiffness. Then you have to define at what load level or what deflection, what strain level your stiffness is. Okay, so then you have concept of tangent stiffness, secant stiffness. This will be called your initial tangent stiffness. But this is more or less straight. So this slope of P versus delta, it's like an elastic spring. This is your stiffness, right? This is K is to stiffness is P. So obviously the slope of the orange line is more than the the slope of the yellow line. So, conclusion is this structure or material is stronger, but this is. I hope that fully answers your question. And often we get confused because we mix up these two terms. I've worked with doctors working on a wrist fixator, and I found this problem with them. They could not really discriminate between angle of twist and torsion. So for the lay person, these terms are interchangeable. In common parlance, we say the stresses and strains of daily life. But there's a huge difference between a stress and a strain. And I expect structural engineers to be sensitive to these differences. Right. Take an axial member. So I could draw this graph for an element, let's say an axial element. Either compression or tension. Let's make it tension so the possibility of buckling is not there. Let this be B. Let its original length be L. And let the increase in length, because it's going to increase in length. Let it be L plus delta. So delta is the axial deformation in the member. Let's say you have this kind of behavior. Let's not decide what is the material. Can you give an expression for stiffness? Yeah? Anybody? Sorry? AE upon it. Just as an example, this K is P by delta. I prefer to write as K right? How did you get it?
It's L by 2.
Okay, so you are right. Your answer is right. And this is also, he is thinking of a factor of half. Where does the factor half come? It comes in energy, strain energy. It doesn't come in. Can you go back to fundamentals and tell me how you got this? VA by L?
From strain compatibility.
Strain compatibility. Now you're getting into trouble.
From the expression of delta, that is PL upon A.
I know everybody knows this formula in a truss element. That's a formula. How did you get it? Very relative answer. I want you to be very strong in your fundamentals. Your answer is correct. I'm going a little deeper and said you gave the answer from memory. As a good structural engineer, you should be able to derive from first principles. So what is what is that law which you will never forget, which you studied in school about elastic behavior? What's the type of law? What's the name of the law? Hooke's law. Right. So we're now talking about linear elasticity. Hooke's law. What is Hooke's law? What is Hooke's law? Right? Hooke's law has two parts to it. What can someone tell me the two parts? I hope you don't mind these digressions because these are fundamentals.
Robert Hooke stated that within the elastic limit, the stress is proportional to the strain.
Wonderful. So he said for an elastic material, what is an elastic material?
Which has nonlinear behavior.
No. What is elasticity?
That's plasticity.
Plasticity is another term. Then you've got yielding. What is elasticity? So we are now going back to basics. What is elasticity?
It is able to regain its shape.
Right. The ability to regain the original shape after the removal of the load. That is elastic behavior. So, which is more elastic, rubber or steel? That's a tough one. Which is more elastic, rubber or steel? The lay person will say rubber band. But structural engineers said no, steel is got a higher modulus of elasticity than rubber. What do we mean by that? So then you have to have clarity. In both cases, it regains its original shape. Okay? But the force required to stretch steel for the same elongation is much, much more. So elasticity doesn't mean rubber band behavior. In the sense it's easy to stretch. It only says when you release the load, it will go back to its original shape. Got it? That's the first part. Then it also says that the stress-strain behavior is linear. That means if a certain actual strain, epsilon, results in an elastic stress, sigma, and if you apply 2 times epsilon, you will get 2 times sigma. That is the principle of linearity, which necessarily requires you to note that that straight line must pass through the origin. Then only the principle of superposition is valid. And strictly speaking, it can go in the negative direction also. So minus 2 sigma will also cause minus 2 epsilon. But some materials don't have the same modulus of velocity in both tension and compression. Clear? Okay. Now, this is true up to the elastic limit. As you rightly said. So the second part, so one part talks of linearity, the other talks of regaining the original shape. And strictly speaking, when you draw the stress-strain behavior, if it's linear elastic, when you unload, it will go back to the original point. So whatever strain and energy is accumulated gets released fully. So the ability to retrace and recover is the property of an elastic material. That's why we say the system is conserved. Now he brought in a factor of half. That is valid for the energy component. What is this energy called? It's called strain energy. And this is half
Sigma square B. Square B.
Sigma epsilon, nothing wrong. Now here the question is which is the cause and which is the effect. So if you have a strain-induced loading, strain is the cause and stress or force becomes the effect. But when Hooke did his experiment, probably he had a spring and then he put some weights incrementally. So that was a load-induced, load-controlled experiment. So traditionally, our rule is the independent variable you put on the x-axis and the dependent variable on the y-axis, but by convention, the physicists have decided that it is not force which is a fundamental dimension. MLT, its mass, length and time. The force is derived from these fundamental units, so force becomes always a derived unit. So we traditionally draw displacement strains on the x-axis and stresses, forces on the y-axis. This quantity also has some meaning. We call it U star. What is that? It's complementary strain. Okay, this is all incidental.
Sir, I may be wrong, please correct it. Sir, you take the upper half of the specimen, whatever you have indicated.
Yeah.
So, center portion is not moving.
Yep.
So, upper half means one is not moving, another will be moved by delta by 2.
Yep.
Now, if you calculate stiffness, you will get D by delta by 2.
Right.
No, I am not talking about EA by
We'll go to first principle. Good one. Well tried. Let's go back to first principle. Right? So we said
Also L by 2
E
is there.
is equal to sigma by epsilon. If you have a pure actual stress, this sigma is P by A. This epsilon is delta by L. That's how you get this. I'll ask you a question. Don't get confused between displacement and strain. Is the force the same everywhere if you got a free body?
Yes.
Is the stress the same everywhere? Yes or no? Yes. So, it follows that the strain is constant from here to here. Now, the displacements depend on boundary conditions. If I were to hold this and pull it, then the strain is constant, but the displacement will take this shape. This is called U. Like this becomes your delta. So, strain in this case will be d delta by dx or whatever you want to do. So, don't get confused. If I hold it in the middle, then the displacement there is arrested. So, this strain. So, these are all important points. So, the displacement depends on boundary conditions, but the strain does not. Clear? This is all incidental. Let's come back to reinforcement.
Sir,
Yeah. Good.
when we're drawing stress and diagram, the angle made by the graph is x-axis. Can we find it by taking tan theta equal to
Wait, you said something. I'm glad you raised this question because there are blunders made even in codes. Don't ever talk of angle. Why? Because. Wait. Very important. I do an experiment. This is an experiment, right? So this is my scale and say 1, 2, 3, whatever units. 1, 2, 3, etc. And I get a line like this. This is my, if I take the slope of this line, that is my, in this case, modulus of plus. I have a friend who doesn't like to do it this way. He says, why should I do this? Let me choose. This is 1, this is 2, and this is 3. He likes to stretch things a little bit. So the same line will now look like this. And if you try to measure this angle, it will be different from this angle. And your tan theta will give you different results. These are common blunders made by students. But you can't go wrong if you take a difference in height here, a difference in width here, and take that ratio. You can't go wrong. Is it clear? So, that depends on your units. But if I put 2 into 10 raised to 5, it's not much. So, you have to use your brains. When you write something in millimeters, it looks big. If you want to write it in microns, it looks even much bigger. So, you want to blow it up, it will look that. If you want to write it in meters, it will shrink. If you want to write it in kilometers, it will just disappear. So, that's why you talk of significant figures. And you don't worry about whether it's 10 raised to plus 6 or 10 raised to minus 6. It doesn't make a difference. So, your questions are good, but they reveal a lot of confusion, and it's fundamental. So all students tend to have. You need to sort out. You need to sift the chaff from the grain. That which is core, that which is the essence, and that which is not so essential. But I'm happy you're asking my question. Any other question? Shall we start? Good.
You told me that independent quantity should be on the x-axis.
No.
So if strain is in the x-axis, Does it mean that the experiment should be a strain controlled one?
Good question. So I'll tell you the story. When Newton discovered his laws of motion, he was very careful. He said force is proportional to what? MA, mass into acceleration. Right? He didn't say it's equal to mass into acceleration. Right? So there's a constant of proportionality. Now, to give credit to Newton, we set the unit 1 Newton force, and we said we'll make the constant proportionality 1 when we talk 1 kilogram mass accelerating to 1 meter per second square. But otherwise, there is a constant proportionality. Now, historically, there has been a difference of opinion between engineers and physicists. For engineers, kilogram was always a unit of weight. For physicists, kilogram is a unit of mass. And so discriminate, we used to talk of kgm, kilogram mass, and kilogram force. Do you remember? And 1 kilogram force is 1 kilogram mass into g. So that g was hidden there. Do you understand what I'm saying? Then later they came to a compromise and said, okay, you physicists, you guys win. Okay, we'll also stick to mass as kilogram, but old habits die hard. And what should be the aim of education? Just a couple of minutes. What's the aim of education? I could take the approach that our job here is to learn reinforced concrete design, and that's it. But half of you will never use reinforced concrete design later. You will be applying for whichever job gives you money and security. Join the railways, and you'll be counting the goods wagons traveling on the rails. So, I really want to add value to your life. Right? So, the whole idea of learning is to improve your ability to learn. So, tomorrow, whatever the future holds for you, you can still approach it with a good analytical mind, a good intuitive mind, a good aesthetic mind, which can go deep and wide into any situation. Is it clear? So this is just a learning exercise. Number one. So our aim is to self-actualize, to really do very well in whatever we're good at. So this is just a tool to sharpen our brains and minds and hearts. Is it clear? So you're free to ask any question. But we'll always come back to reinforced concrete. But you're welcome to that. Okay. So this is our first module. Today we will quickly cover introduction to plain reinforced concrete. Then we look at the other topics. Concrete is the most commonly used construction material, consumed at a rate of approximately 1 ton for every living human being. That's massive. And concrete is massive. Man consumes no material except water in such tremendous quantities. This is a harsh reality. That's why concrete is so important. In India, most structures are built with concrete, but not necessarily in all other countries. In the US, they use a lot of steel. Steel is not very popular in India, though they are trying hard to popularize it. Why? Simple question. After studying this course, if someone asks you this question, you should be able to answer. General knowledge. Why is concrete so popular and steel relatively not so popular? Raise your hands. That's the right way to answer. Yes.
It's more expensive.
More expensive. Steel is more expensive.
Yeah.
Okay. It's cheaper in the US?
No, maybe. Yes, it's easier.
No, you're missing something. You're right. Finally, everything boils down to money. Right? Everything boils down to money. So, whichever is cheaper has a greater chance of being more popular. Why is it cheaper in India? And why is it more expensive in the US? Labor is very expensive. Labor is very expensive. So, in any construction cost, you have material cost. You thought concrete and steel is only material. Then you have labor cost. India is a very populous country with a lot of poor people. The easiest job you can get, and by the way, if you happen to do badly in your subjects, one job you can always get is construction industry. Unskilled, skilled, different levels, right? People work. People work. And labor, it's good to have labor intensive work to give occupation to people, right? So labor is much relatively cheaper in countries like India, and that's why concrete is so. And of course, with mechanization, we're reducing the labor, but you'll still find in India more people hanging around for over every job where less people could do it. Whereas even in Europe, you have very few people working, right? Okay, so that's clear. That's why. What is concrete? What is concrete? After finishing this course, you should answer at least this question. Huh?
Cement, aggregate, water.
Again, let's go back to generics. Oh, generics. Generic. If you look up the dictionary, what does the word concrete mean? Will it say mixture of cement, sand, steel, whatever you've been taught? What else? Cement, aggregate, water. But even that's not today the definition of concrete. But leave that. What's a more generic definition of concrete? Have you got any concrete answer to give? That's a valid question to ask in any subject. But there you don't bring in cement, concrete, cement, sand and aggregate and all that. But I thought concrete is cement, sand and aggregate. What is this concrete? Right? Solid. And really it's a miracle how by mixing, you said mixture, no? You mix sand. Let's say you mix sand, coarse aggregate and water. What will you get? You'll get concrete. When the water dries up, you'll get back the same mixture, right? It's not solid. It's a miracle that all these highly separate pieces of solid matter, of earth. We talk of Panchabhuta. This is really earth, one element. That one element, all these discrete things can become one solid element. We wish that the country, the world is like that. Different nations, different religions, different people can also be a bit like concrete, which they don't. They can become one. They're all separate, all fighting. If the elements in concrete become like human beings, then things you can't build any buildings or nation. So, concrete means something solid. It also means something that is a simple layman's language. Not only you say, God, this is a concrete suggestion, concrete idea. What's good about something solid?
Change it.
Huh?
Should not change.
Doesn't change the form so quick. Everything will change. That's a law of nature. Who said it? Well, two great people in the West. A Greek philosopher called Heraclitus said, when you step your foot in the river, and the next time you do it, it's not the same river, it's not the same foot, it's not the same person stepping. Everything changes. Everything changes. And the other great person who kept harping on it is Gautam Buddha. Nothing is solid. Everything changes. Everything changes. Change is the law. Change is the law. But we are saying relatively slowly. That's all we are saying. So slowly that it lasts for some time. Right? So what's that property lasting in time called? It's a beautiful property. Durability. So concrete is solid. It is durable. It can be cast into any shape easily. Right? Durability also in concrete, we also know how durable. How durable is a concrete building? How many years?
100
years, if you're lucky. 100 years. If you put steel in it, you'll be unlucky because steel is the weak point inside concrete. Okay, good. So, concrete is something solid, something durable, it can be cast easily, and you can put it into any shape. Okay, basically. It basically is any solid material that you can make using a cementing medium. Today you can even avoid cement, Portland cement, and still make concrete. You need this aggregate and you need a binding agent. Tomorrow you can come up with your own binding agent. Okay. And things are changing. Sand is not available. River sand is not available. So we have to manufacture something that looks like sand. But usually you take stone and you break it into pieces. So basically you've got stone and you've got a cementing agent. Okay. Now can you give me some applications of concrete? Today, when you reach this class, you made use of many applications of concrete to come from your hostel room here. Name them. Pavement, I'm not sure if you walked on a concrete pavement. You're imagining things, but anyway, hopefully there are concrete pavements in IIT, maybe near the hospital. I hope you didn't have to go to the hospital there. You have a concrete road there. Okay, you walked on that. Pavement, it's the first thing that comes to your mind. My God. Where do you live, by the way? Outer space somewhere? Where? Bird's nest? Hostel. Hostel is how many story building? 3-story building. Where is concrete? Did you walk on concrete? Did you? The slab. Where do you sleep at night? On a bed. The bed sits on a concrete slab. Is it a solid slab? Is it durable? Yes, that's why you can sleep peacefully at night. Is the slab above you sagging? How to fall down? No, it's solid. So you're lucky. So your whole building, at least the slabs, maybe the walls are masonry, the columns, the beams. So where you live is a concrete structure. Got it? Okay. What else? What do you do when you wake up first thing in the morning? Hopefully you've had a bath, I hope. Okay. So how did that water come? Pipes. Pipes. Huh? Where was the water stored? Water tank. How did it reach that water tank? So you'll find that concrete is used in storing, in supplying. Your pipes are small, they are not concrete, but you have large hume pipes also. So concrete is in storing water. That's because it's durable. Otherwise, the concrete, you'll be having your bath in concrete if cement and all slips out. Right? So, okay. What else? Did you switch off the lights when you came? Switch on? How did you get the electricity? You never think of these things. No gratitude. Where did it come from? Hydropower, you're saying. All power plants use massively concrete. So in short, everything is concrete. Though we take it for granted. Okay. Buildings, stadia, auditoria, pavements, bridges, breakwaters, jetties, dams, waterways, pipes, water tanks, swimming pools, cooling towers, bunkers and silos, chimneys, towers, tunnels, nuclear reactors, etc., etc. You can fill in them. So, concrete is really material we need to understand. To use wisely, to use economically, See, there's always a trade-off between safety and economy. You must know how to intelligently use concrete. Concrete may be defined as any solid mass made by the use of a cementing medium. Look at this definition. It's a beautiful definition. But all of you have been brainwashed into saying, no, it's a mixture of sand and aggregate and water. No, this is the actual. The ingredients comprise sand, gravel, cement, and tradition. Its success in popularity may be largely attributed to durability under hostile environments, ease with which it can be cast into a variety of shapes and sizes, and its relative economy and efficiency. Simple. The main strength of concrete lies in its compression bearing ability. Very commonly, natural materials are good in compression, but they are weak in tension. Bricks, stone, earth, mud, compression. But tension, all of them are weak. Which are the natural materials which are strong in tension? Wood. Wood is good in both compression and tension. Then steel. You get steel when you dig the ground, you get steel. Well, steel has to be manufactured and there's a lot of energy that goes into extracting the iron ore and processing it and but still, right. Other things you can pick up from the ground and do it. Okay, steel. Early days, what did they use? Huh? Okay, fiber. Natural fiber. Coiled, jute, ropeways are made of that. So, the compression bearing strength surpasses that of traditional material like brick and stone masonry. So, what is the compressive strength of concrete? What is the compressive strength of stone? For example, you don't swallow what is written in the book. You have to have some feel. What's the compressive strength of concrete? Huh? Give me some number. Give me a range. 20, 30, 40, 50, 60. What? Huh? You are saying Newton per millimeter squared and you are saying megapascal. Are they two different things or the same thing? Sure.
Yes.
So you see, you are pointing at the same thing using different words. Okay, megapascals is now the better thing to write. What is 1 Pascal? Who was Pascal by the way?
Blaise Pascal.
What is Pascal's law?
Pressure is aligned will be distributed in each value actually.
Equally. It's important to know that. I'm sorry it's a digression, but I want to tell you something which actually caused distress in a water tank which was built. Well, engineers should know that. So there was a water tank which had a shape like this. Okay. And the water level was here. So water finds its own level, you have atmospheric pressure here. And this was done by a structural engineer. It's a big company, I won't tell the whole story to avoid embarrassing the people who did it. But the person who designed this, I first saw it in the foundation, that said this was 8 meters. So what's the water pressure here? Can you tell me? Inside? It's good. How much of water pressure? How much of water pressure? Huh? What's this pressure at the base? See, you're in MES. These guys are old timers. 50 years ago, whatever their bosses said, they still talk of kg. We are now in pascals. So talk about unit of pressure is pascals or megapascals, right? Tell me how much is it? 4 kilonewtons. Tell me. How do you find pressure?
It's rho.
8?
It's rho.
H rho G. Okay.
Plus and plus.
Atmospheric pressure is not our inheritance. Tell me how much? 80 kilonewton per meter square. Agree? Because the unit weight of water is 10 kilonewton per meter cube. Remember, concrete is 2.4 times that. 10 kilonewton per meter cube. That into height will make it kilonewton per meter square. 80. Then I noticed this guy had imagined a pressure distribution like this here. So let's say this is 6 meters. So what will be this pressure? 60. Is this correct? This is an RC slab. Correct or not? It's wrong. But after because tank was built and distance was noticed, we realized that he had assumed in the foundation that the pressure in the floor below is like this, 80 here, suddenly dropping to 60 here, and then going back to 80. Now, if you take that point there, you can't suddenly change pressure from 60 to 80. You're violating Pascal's law. Pascal's law says the pressure is the same in all directions, which is why if it was 8 here, it's 8 here. So this is wrong. And to cut a long story short, this should have been the pressure distribution. And the same pressure distribution holds good here. And you actually end up with a pressure here, which means you have an uplift here, which was not designed for of 20 kilonewton per meter square. So you can make serious blunders if you don't know Pascal's law. You may think that I am doing concrete building, I don't need to know Pascal's law. You need to know Pascal's law. It's fine. Serious mistakes, you'll have an uplift. Okay. So, why did we talk about
Definition about Pascal. Definition of Pascal you are asking.
I forget.
Basic strength of compressive strength of concrete and stone.
Yeah, so what's the allowable strength in brick masonry? Say you're checking out the strength of a wall. You want to know whether 230 mm brick wall is good enough to take a load in a load bearing building. What's the brick strength that you usually use? You can always link it to concrete. Concrete is say 20, and this will be about 5, right? So it also depends on whether it's wire cut or country brick and all. So that's why we say concrete is much stronger than conventional materials. Concrete may be remarkably strong in compression, but is remarkably weak in tension. So in the early days when they worked with concrete, they found that it couldn't take any load as a beam because it ruptures. What is the stress at which it will rupture? What's the name for that? Modulus of rupture. It's the flexural tensile strength of concrete. So, how do you make this work? Well, you put steel in it. Right? Why do you put steel inside concrete? To make up for its inability to resist tension. So, but luckily this combination works well for many reasons. What are the reasons? What are the reasons that this works? Similarly, if you've broken your leg, they do implants. They use titanium. They even use special grade stainless steel. Why does it work? Not all materials can be combined. It works because
They have the same coefficient of thermal expansion.
they have the same coefficient of, more or less, not exactly, coefficient of thermal expansion. Very important property. What else? They bond to each other very well. Bond is absolutely important. These two, steel and concrete. steel contributes not only to tensile strength, it gives another property to concrete which is badly missing in concrete. What is that? You can see it in this graph. That property. Ductility. Concrete is a brittle material. It will break. Steel is a ductile material. It can stretch. So the combination brings ductility. Why is ductility important in buildings? It gives warning. Warning for what? It rings a bell. No, you're talking about under-reinforced behavior. No. Ductility is very, under some kind of loading, that's really helpful. What kind of loading? Earthquakes. How does it help?
Steel might be like rapidly undergoing the
Prolongs the damage. Slows the damage. Huh? Give me a correct answer. How does ductility help in earthquake resistant design?
Energy will dissipate.
Very good. See, the earthquake is pumping in energy into the structure. The structure, if it were to behave elastically, will store that energy and release it. But the amount of energy does so huge, it can't do it. Right? So it'll break. There must be some way to get rid of that energy. That energy is got rid of through many ways. Extensive cracking will release energy. Damping will release some energy. But more important, yielding of steel. So steel is yielding, and steel has this fantastic ductility property where it can go on yielding for a long time without letting go of its strength. That's called plastic behavior. And heat is generated in that. So, that's how the energy is dissipated. It's absolutely necessary. So, ductility is the way. And here you get cracks. This room has got a false ceiling, but if you were to see the beams there, those cracks are not visible. Otherwise, occupants in houses will complain. But cracking is unavoidable. Concrete will crack. So the crack should not be perceptible. So what's the crack width that is allowed in codes so that you don't see it? 0.3 mm, very good. 0.3. So if you had to say 0.3, okay, and you didn't, so your 0.003, you have to then put your 10 raised to plus 2, then you'll be happy. So we'll give you that correction, you just have to add some. So you can always make up by adding this 10 raised to plus or minus and make up. Okay, good. The steel bars are embedded and it remains nearly horizontal. The deflects are also not visible. The beam supports load with acceptably low deformation that occurs. Then we'll introduce pre-stress concrete. Now, pre-stress concrete has a history which is as old as reinforced concrete. In pre-stress concrete, we apply some pre-compression into the concrete so that you delay the tension, the tension doesn't develop, and the beam supports load with very small deformation. We'll study this in detail later. So, this is how behavior takes place. Concrete is actually not a homogeneous material, you know that. If you look at the microstructure, it's a mixture, as you rightly said, but it's still solid. And if it has to have the same properties, if you want to model it as a homogeneous material, then these different particles should be more or less uniformly distributed across its medium. And that you can study from microstructure. So you have coarse aggregate of gravel, fine aggregate of sand, and you have binder, which is hydrated cement. So this is concrete technology. It's a big course by itself. It's something that you should know. I'm not going to cover it much, except to tell you that both good concrete and bad concrete can be made exactly from the same ingredients. So it's not just the materials, it's the know-how, how to make it. For example, how many of you can cook? So if you were to bake a cake, some people, and you give the same ingredients, some will give a cake that you love to eat again and again, and some you wouldn't go near. Why? Ingredients are the same. Same is with concrete. You can have bad concrete, you can have good concrete. If you had to select a single measure for concrete quality, which property would you use?
Strength.
Grade of concrete. Grade of. Let's say you're an MTech student from IIT Madras, MTech in structural engineering. And I have to ask you only one question to assess, one area to assess. You're studying steel, you're studying concrete, you're studying analysis, you're studying structural mechanics, dynamics, theory of plates and shells. But I want to quickly gauge you, so I will ask you some questions in some areas, right? Likewise, concrete has many properties, many desirable properties. But you want to make a quick assessment of the overall quality of concrete, and they must be more or less correlated to this fundamental concrete property, right? Which property? Another thing, if you want to quickly test, you must be able to test it easily also. So what's the one measure of quality of concrete? Compressive strength, and that's its greatest strength. So yes, the desired properties of concrete are its compressive strength, tensile strength, shear strength, bond strength, density, impermeability, durability, etc. But among these, the property that can be easily tested and is perhaps the most valuable from the point of structural design is compressive strength. This is measured by standard tests on concrete cubes or cylinder specimens. Right? In India, we test cubes. Which is a better test, cube or cylinder? Huh? Cube is better because India is the greatest. Why is cube better? It looks better, symmetric from all sides.
Coordinate system, rectangular.
And if you want to measure compressive strength, actually the cylinder gives you a more accurate assessment of compressive strength than the cube. Do you know that? Why? We'll see this in another module, okay, the next module, but it's important to know. Will you get the same strength when you do the cube and cylinder? What's the size of the cube?
15 centimeters.
15 centimeters. See, you must be consistent in your units. We are using SI units. You stay with millimeters. Didn't say anything wrong. 15 centimeters. It's 150 millimeters. 150 millimeters. 150. And cylinder? 150 millimeter diameter and height. Many of the other important properties of concrete can be inferred from the compressive strength using correlation that have been experimentally established. For example, modulus of elasticity is related. What's the relationship? 5,000 root FCK. Okay. Does the 5,000 have units? No. I told you Newton's law itself, there was a unit proportionality. What is the unit of modulus of elasticity? Newton per millimeter square. What is the unit of FCK? Newton per millimeter square. Huh? But we put one square root there, no? So then what happens? So 5,000 must also have units of square root of Newton per millimeter square. You should know all this. Dimensional homogeneity. And it's 5,000 only in this version of the code. Earlier was 5,700. So they keep revising because test data show better correlation. Okay. Concrete strength is notorious for its variability. It's a strong statement. Notorious for its variability means what? Unreliable. Why unreliable? I give the same ingredients. You make concrete, same concrete, you get one strength. You make, you get another strength. You make, you get another strength. You make, you get another strength. You make, he's the best concrete maker amongst us. He alone makes. But from all that he's made, if you take some little, you don't get consistency. This cube gives one string, the next cube gives another string, next cube gives another. So that's not good. Right? That's not good. That's what we talk about. That's how we use the word variable.
How many minimum specimens you have to test for?
That we'll come to that. How many minimum? So he's asking a question. Let's say you're a mechanical engineer. Let's say, forget concrete. They are saying 3. Round number, that's right. What should it depend on? What should it depend on? Whether to take 3 or 10 or 100, what should it depend on? Cost. Yeah, that's true. In practice, that's what it is.
Out of 100 specimens, any 3 specimens, if we take, there must be more than 15% the difference between the compressive strength.
Wait. Okay. So, let's say you want to buy shirts. Nice shirts like the multicolored shirts. But you want it to be stitched well. Right? You're a mechanical engineer, you're very sensitive. You'll always pull and see when the buttons come off or not. Right? So you want to buy 1 million shirts. 1 million shirts. That's the order you're giving. How many shirts will you test? 3 shirts? How many? You use your judgment and tell.
Some random load will take.
Random sampling you'll do. How many you will test?
Minimum 25.
Minimum 25. How many will you test? 1 million. By the way, in case you didn't know the digits, 10 raised to 6. How many will you test? 10 raised to 6. How many will you test?
7.
Huh?
7.
7?
Yes.
Lucky number. So it depends on many things. One is, let's say the manufacturer is a totally reliable manufacturer. Then you can reduce the number of samples. Right? But even if it's a very good manufacturer, if you are supplying so many shirts, well, you will get complaints if they don't work. You should have some correlation between the population and the sample. So, if you want to really answer the question, please study statistical quality control. It's a huge topic by its. You cannot just say, I'll test 3, I'll test 7, I'll test 25. It depends on many factors. Okay, and the code gives some numbers, but still you have to use your judgment. It all depends on the large volume, the size of the volume, and the importance of the structure that you're going to use. So it's not an easy answer. 3 is absolute minimum for convenience. But sometimes you have to test 30, sometimes you have to test 100. It depends on specific application. Yeah? Any other questions? But these are good questions to ask. As a designer, how would you specify concrete grade? You say M. What M? Add the number. M. No, M1. M30 shall be taken. M30. M30 concrete. What the hell does it mean?
30 is the characteristic strength in concrete.
30 is the characteristic strength of concrete. What is that characteristic strength?
That
You are going to memory.
less than 5%.
All that complicated. What is M30? Compressive strength of concrete. That means if I test all the cubes, I'll get 30. I'll get. So how do I decide? How do I decide? What is M30 concrete? Characteristic FCK. How come they use K for characteristic? Because the people who did it were Germans. Okay, that's why it's true. FCK. characteristic strength of concrete, right? What is characteristic strength? It's just a word. What does it mean? What is characteristic strength? Huh? 95% of the will satisfy the strength required. I'm asking you simple. What is M30 concrete? Answer in a sentence. The sentence is a sequence of words that make sense. What is M30 concrete? Now everybody's careful. It's good, but still try.
M mix design.
M stands for mix. Mix design. Very good. Okay, so we come to the answer. Here I asked question in 20 minutes. So let's look at some fundamentals. Quality control makes a big difference. So whenever you have dispersion, in statistics we use two terms. Dispersion and central tendency. There are measures of central tendency, there are measures of dispersion. Give me 3 measures of central tendency. Let's see if you can remember your statistics. Mean, median, mode. I won't trouble you by asking you what they are. What about dispersion, variability? Standard deviation, variance. And they are the same thing, yeah. Standard deviation where one is the square root of the other. Yeah. Range. Coefficient of variation. What is that? Good one. Yes, you're right. We'll trouble you with that question later. Okay. Now, let's say there are 3 manufacturers of concrete and both all have the same mean strength. You will find that you have to be careful when you buy concrete from this guy. Because you don't know what you will get. You could get higher strength than all these guys, but you never asked for it. And if you were to test your 3 cubes and got these strength, you will jump up and down in excitement. But the next 3 cubes could be giving you these values. Totally unpredictable. Like the answers some of our students give. Right? That's not good concrete. So, with this red guy, you should test more samples. Now you get it. So don't have some rule, 3 samples for all. And if he's clever, he'll give you, he knows which 3 to give you. Okay. Whereas the yellow guy is better. You won't get anything lower than this. You won't get anything higher. Why should you give higher strength than what is asked for? You're ordering the concrete. If you want only so much, I'll give you only that much, maybe a little more. The green guy is the best of the lot. In the sense, he has the minimum, he has the least dispersion. Got it? So, you now understand the influence of quality control. Now, as an engineer, you're a designer. You're trying to design a structure and people are going to build it. But after they build it, you must get what you asked for. So you want some minimum guaranteed strength. You don't care who the contractor is. You don't even know who the contractor is. It has to be tendered. So what's a reasonable way of knowing concrete to be notorious for its variability? As an engineer, I'm glad we have an outsider here, mechanical engineer. Okay? This is not like steel. Concrete is a troublesome material, but a beautiful material. How would you define? He is the best person to answer. We've already been contaminated with whatever crude learning we had in our BTech. He is an innocent outsider. Tell us. How would you? We want to, the designer says, I want to be sure, whoever be the contractor, whether the contractor is green, yellow or orange,
From the center one, that is blue.
you have no choice to prefer because you are doing the design. MES man is going to do the construction. Your preference has no choice. No call, you can't insist on it.
What we check?
No, so in your design itself, you can insist on something. What will you
Standard
insist?
deviation, I will.
No, you can't do those things. The clue is you can specify M30 concrete, M20 concrete. So the definition itself you should capture. You want minimum 30 Newton per millimeter square, 30 megapascal. How do you ensure?
So that is including the standard deviation minus it should be 30.
Tell me what
The minimum value should be.
See, I'll put it this way. You have no choice who will get the contract. All three can get it. So they go by lowest tender. Also, he's been bragged by the orange guy, he might get the job. But even if he gets it, you want the building to be safe. Yes or no? Yes. So how will you specify? This is very important.
Minimum strength.
Minimum strength. Beautiful. What is minimum? Yeah, this thing, you've heard of normal distribution. What is minimum in a normal distribution? Minus infinity. So minimum is a difficult word to use. So you understand. So you have to make the minimum practical. A practical minimum. What will be practical? Actually, he's converging to it. What is the practical minimum? You know that you have to take some risk. Yes or no? This is a risk. There's a risk here. No question about it. How much risk can you take? Risk.
How much percentage?
No, when you said minimum, you could get a value lower than that. So you're willing to accept that risk. How much percentage of your sample size can be below that? 5. Congratulations. He is the original discoverer of characteristic strength. Okay, so that's it. That's how it works. Characteristic strength is defined as the strength of the material below which not more than 5% of the test results are expected to fall. Got it? We did it from first principle without going through the bad mugging up that we went through. He did it from first principle. So it's also called 5 percentile strength. When you have data dispersed, 50 percentile is the median. 5 percentile strength is the characteristic strength. That means if you were to have a distribution, very rarely you get a perfect symmetric Gaussian distribution. But if you get a distribution like this, you're saying, yes, this could stretch and obviously this can't go below 0. You can't get a negative strength. So you have to, this is the lowest value you can get. But this is a risk you're taking, the shaded area. And so we say that this is the characteristic strength. So your mean strength should be much higher. But that's not your job. The designer doesn't specify mean strength. The designer specifies only characteristic strength. And the mean strength will be controlled by whoever supervises the construction. And he has to make sure whether the contractor is green, yellow or red. Obviously, if it goes to the orange guy will have to have a higher mean strength compared to the other two. Right? So now you're getting the hang of it. So the mean strength is given. So if you assume this to be a normal distribution, which is a big assumption, then by the properties of the areas of the normal distribution, you will find that this is 1.65 standard deviation away from FCK. So if you were to design the mix, you should find out from your past history what's your standard deviation. And then 1.65 times the standard deviation plus FCK is your target mean strength. Or you could work backwards like this. Is it clear? So the area is 5% here, the rest is 95%. So that's the minimum. Got it? Now I have
28 day composition.
28 days. Because concrete sets quickly. Then you remove the shuttering. Then it gains strength. Okay? And the rate of gain of strength depends on many things, especially the fineness of the cement. But we hope that after 28 days it more or less stabilizes. You have a standard. See, so on the 28th day you test. After 28 days also you might get a little gain in strength, but we ignore that. Is it clear? That's the 28th day gain in strength. Okay. Now I have a question. What is coefficient of variation? Who said coefficient of variation? Oh, okay. We'll come back to you. I have now two contractors here, you and you. He produces concrete with a standard deviation of 3 megapascals. He produces concrete with a standard deviation of 5 megapascals. Who is the better contractor? Sure. Not necessary. He's happy. Not necessary. He's a low time, low budget, small contractor who's never cast concrete more than 20 megapascals in his lifetime. With 20 megapascals, he's getting 3 megapascals as standard deviation. He is a big time contractor. He does only concrete which is M80 and above. Super tall buildings. And there he's able to get 5 megapascals. Now tell me who's a better contractor. Out of 80, only 5 out of 23. If you give him that 80, he'll get a standard deviation of 12 or 14 or something. So you jumped into a conclusion just by looking at the raw numbers. You have to always link it to the mean. That's where coefficient of variation comes. Coefficient of variation links the standard deviation to the mean strength. It is actually the ratio of the standard deviation to the mean strength. It's a non-dimensional quantity which you can sometimes multiply by 100. So in general, you could say, if you can get a contractor who can give you less than 10% coefficient of variation, decent. Who's giving you 20% bad, giving you 15% moderate. There are some very good contractors who can give you 8%. Now you get the hang of it. So, once you have a mean strength, you also know that this cannot stretch plus or minus 3 sigma. You will cover 99%, 99.7% of the sum. That's how the lowest value and the highest value you have some idea. Okay? Now, how do you decide the grade of concrete? Well, the code says it depends on exposure condition. So, if you could have 5 grades of exposure, you have mild exposure. This is IS 456. Mild exposure, moderate exposure, severe exposure, very severe exposure, extreme exposure. So this is the first question you should ask. When you're designing, you should specify the grade. The grade is based on the durability aspect. How badly exposed. Let's take mild. Mild is protected against weather or adverse conditions except if located in the coastal area. This is the lowest grade M20. In some countries it's M30, M35. I know in Canada it's M30. Sheltered from severe rain or freezing while wet, exposed to condensation and rain continuously underwater, in contact with or buried under non-aggressive soil or groundwater, or sheltered from saturated soil area in coastal areas. This is moderate. Severe, exposed to severe rain, alternate wetting and drying, or occasional freezing whilst wet, or severe condensation, or completely immersed in seawater or exposed to coastal environment. M30. This is what I would recommend for Chennai. We're on the coast. So M30 is what we. Sometimes some parts of the same structure you can specify a higher grade. For example, the external facade, the columns which are exposed, and the interiors treat as moderate or mild. Very severe exposure. See water spraying, corrosive fumes of severe freezing while wet or in contact with or buried under aggressive subsoil or groundwater in 35. And members in tidal zone. Tidal zone means the worst thing that you can have is alternate wetting and drying in saline. Members in direct contact. So you will find the worst damages take place when you have these jetties and piers, they are constantly exposed. And the salt spray is another load on the structure. With time, all these increases as you increase, you want more durability. So, in the earlier code, we had N15 as a minimum grade, now we have N20. This is for reinforced concrete. For pre-stressed concrete, strength also matters. So, M40 becomes a minimum. The design of a concrete mix for a specified grade involves the economical selection of the relative proportion and type of cement, fine aggregate, coarse aggregate, water, and admixtures. The mixed design is by itself. Although compliance with respect to characteristic strength is the main criteria for its acceptance, it is implicit that the concrete must also have the desired workability in the fresh state and impermeability and durability in the hard state. So these are the four properties which are most important. In the hardened state, you want strength, you want impermeability, and you want durability. Durability and impermeability are linked. But usually you can do that by minimizing your water cement ratio, reducing your water content, but then it becomes a harsh mix. You can't mix it easily. So workability is what the contractor is worried about. It should be workable. You have to work on it. You have to mix it well. You have to compact it. So this part, the hardened state, is what designers are obsessed about, and the green state, when it's still a fluid hardening, is what the contractor is working. So this is again something you can read up in the textbook. So I've been told next time. Let's see what's the next topic. We'll just finish this. We'll start pre-stressed concrete later. We'll just wind up. Right. So the other code that is worth looking at is IRC 112, Indian Roads Congress, which is a more recent code, which is actually for bridges, and it's actually directly related to the Euro code. So here we have different types of concrete: ordinary concrete, standard concrete, to M50, high performance concrete, M30 to M90, where this number is always strength in megapascal. What is the difference between high strength concrete and high performance concrete? Good question. What's the difference? Both are high. What's the difference? High strength does not necessarily guarantee high performance. In high performance, your emphasis on lifetime, on durability. So standard concrete is made on the basis of design mix proportion by weight in addition to cement, aggregate and water. It may contain chemical admixtures. That's to improve workability. You have accelerators, retarders, plasticizers, etc. to achieve certain target values of various properties in the condition. Generally, concrete up to 50 grade is put in this category. What about high performance concrete? High performance concrete is similar to this, but contains additional mineral admixtures. These are chemical admixtures, superplasticizers, etc. to make it workable. But this is to make the microstructure more compact, to reduce the voids, so that there's no ingress of water or chemical attack. And so this is possible when you add special admixtures, fly ash, silica, fume, rice husk, ash, etc. to increase strength, reduce porosity, etc. Concrete up to grade N90s. Okay, so we'll stop here. We'll take up pre-stress.